I'm Valérie Leprince, and I will present you the work that I have been presented to the AIVC 2019 conference in Ghent about the deviation of blow-water fans over year. So, our objective here was to evaluate fan deviations over year to know which calibration requirement shall be put on blow-water fans. To do that, we have gathered calibration certificates from certified bodies, mainly from UK and France, where the calibration is mandatory every year in UK and every 2 years in France. And with those calibration certificates, we have evaluated the deviation of the fans, of the blow-water fans. In the first part of the study, what we have done is we have done like a systematic adjustment of fan coefficient, which means that we have recalculated the C and the N coefficients of each configuration for each fan, for each calibration, and then calculate the flow rate. We have done it at year high, and then the same thing at year high plus G, and we have plotted the deviation between year high and year high plus G. In the second part of the study, we have done it in the French way. That means with no systematic adjustment of fan coefficient, but with keeping manufacturer coefficients. Well, in France, they keep them as long as they are good enough. So we have compared the flow rate given by the device with the manufacturer coefficients with the flow rates given by the calibration device. And we have plotted the deviation also. At the end of the study, we have also estimated the impact of the calibration uncertainty on the results. So we had 4 sources of data. One is the Stromatec, which is a calibration laboratory in UK. The second one is Cerema, which our tester would depend on the French Ministry for buildings. So they are not using their fan very often. It's more for research projects, so it's a few times a year and not every day. We have also data from Cineal, which is a trade union of airtightness testers in France. So there are fans that are really used every day. And we have also data from BCCA, which is a certification body in Belgium. For the first part of the study, it was much more difficult to gather data because we needed that the fan have been calibrated at least twice in a certified laboratory to be able to plot the deviation between the first and the second calibration. So for this first part of the study, we have 12 fans only and up to 10 configurations per fan. Some of them have been calibrated more than twice. So at the end, we get 153 values for the deviation after 2 years, so which is, well, the more data we had, so we have performed the statistics for the deviation after 2 years. For the second part of the study, it was much more easier to gather data because each calibration certificate can be used even if the fan has been only calibrated once. So we have used 62 calibration certificates. Each of them have up to 10 configurations, so at the end it's 325 configurations. And each configurations are tested at least 3 times for 3 different pressures. So we had 1,007 data to perform the statistics. So let's move on to the results of the first part of the study. So first of all, something very important to keep in mind is that in this first part of the study, we do not only see the deviations of fan, but also the calibration uncertainty. Because there is, of course, the calibration uncertainty at year high and at year high plus G also. And the error due to the linear regression for the calculations of coefficients, because we were doing linear regression to recalculate coefficients. And we have found out that those coefficients may not be very good because we have seen that there were a large impact of the pressure used to calculate the flow rate here on the results of the deviations. And the smaller the pressure is, the larger the deviations. If we were using only 50 Pascal, we found out that 10% of fans were deviating of more than 10%. While if we are using 150 Pascal, which is more or less the average of the pressure at fan, it's only 6.5% that deviate of more than 10%. So the linear regression with only 3 points may induce also a large error in this study. So as I said, in the first part of the study, we found out that 10% of fans deviate of more than 6.5% after 2 years, and 5% of fans deviate of more than 8% after 2 years. We have also plotted the positive and negative deviations, and we found out that the flow rate measured by fan vary, there is a very small increase of this flow rate, but mostly it varies randomly around zero. Also, we have plotted the deviation according to the data provider, and we found out that the fans from Cerema, who are well stored and little used, deviate much less than other fans. We see that 100% of the fans from Cerema deviate of less than 4%, which is very, very low. We have also plotted the deviation according to the flow rate of the configuration, and we see that small flow rates deviate much more than large flow rates, with 10% of small flow rate configuration show a deviation of more than 8%, while for large flow rates, it's only 4% that deviates of more than 10%. Let's now move on to the second part with the result of the comparison with manufacturer coefficients. So, first of all, we have found the same result regarding the deviation according to the flow rate, with medium and large flow rate configuration, which have a similar low deviations, 4% deviate of more than 5%. So that means that 96% remains conform to the requirements for medium and large flow rate, which are without ring or with open or ring A on the blower de fan. We see that small configuration also have a higher deviation, with 10% that deviate more than 7%, but the maximum permissible error, at least in France, is also higher, because it's 2 cubic meter per hour or 5% the highest, and for small flow rates, sometimes 2 cubic meter per hour is higher than 5%. We observe the same difference according to the data provider. Like for the first part, the Cerema, who have provided the 204 data out of the 1007, were little used and well stored fan deviate much less than daily used one. But it's also a bit biased, this statistic, because the fan of Cerema are not representative of all the calibration laboratories and all the devices used in the market. Interesting results come with the background test pressure. When a building airtightness test is performed, the pressure between inside and outside the building vary between usually 10 and let's say 50 or 70 Pascal. And so when a calibration laboratory is performing a calibration, they also impose a pressure difference between inside the calibration chamber and outside, on both sides of the measuring device. Usually they use 50 Pascal as a background pressure, but there is no requirement on that, so some of them use 30 Pascal instead of 50 Pascal as a background pressure. And we found out that with a 50% background pressure, 10% deviate of more than 3.5%, and 5% of the fan deviate of more than 5%, which is very, very low. But for the certificates with a 30 Pascal background pressure, we have a much higher deviation, with 10% deviate of more than 5.5% and 5% of more than 15% here. So it seems that the fan's coefficients are mostly suitable for 50 Pascal, and so when performing a multiple test on site, maybe there is also an additional uncertainty due to the variation of those coefficients with the background pressure, and that shall be included in the global uncertainty. So we really need to have further investigation on this subject. Now let's come to the last part of this presentation about calibration uncertainty. We have plotted here the capability index of the laboratories that are performing the calibration. The capability index is the ratio between the maximum permissible error and the calibration uncertainty. Basically, when you are calibrating a device, you assume that the uncertainty of the laboratory is much smaller than the maximum permissible error of the device you are calibrating. If you want to reach maximum 5% of error, you assume that the laboratory has an uncertainty below, let's say, 2%. And usually what we say is that this ratio here shall be above 3. So that means that the maximum permissible error is 3 times higher than the calibration uncertainty. If it's below 1, it means that the reference device used is less accurate than the measuring device under calibration. And we have some data here below 1, so it's quite depressing because that means that the reference is worse than the device under calibration. We see here that most laboratories have a capability index between 1 and 3, which is quite bad because it means that the reference uncertainty is quite equivalent to the MPE of the device. We have some laboratories, some data here between 3 and 6, which is good, but we see that we have very little data here. And some of them that are above 6, and it's quite worrying also because it brings a question on the estimation of the uncertainty by the laboratory, and we can ask ourselves whether it has been correctly estimated and how every part of the uncertainty has been included or not. We have plotted here the deviation according to the calibration laboratory, and we found out that laboratories which have a low measurement capability index, here in purple and blue, also have a higher deviations. But those results may be biased by the fact that these laboratories also check only a certain kind of products and they are not checking every kind of devices. So it may be based on this statistic. We have also plotted the deviation compared to default coefficients with whole data in red and only data with low calibration uncertainty. So that means with the capability index above 3. And in fact, we found out that data with low calibration uncertainty have higher deviations than whole data, which means that, in fact, so if we take only reliable data, it deviates more than whole data. So in fact, the deviation we observed here is not due to the calibration uncertainty, and there is really a deviation of the fan that appear after years. So as a conclusion, I would say that the deviation is quite similar in the first part with the recalculation of coefficients, and in the second part, using manufacturer coefficients, we see that in part 1, 10% vary of more than 6.5%, and it's 4.5 in part 2, and 5% vary of more than 8% and 8.5% in part 2. So this is quite similar. We also found out that 6.5% of the configurations do not comply with the French requirements, which means that one certificate on 10 gets at least one non-compliant configuration. So one fan on 10 needs a calibration because it is not compliant with the regulation. So the flow rate measured by fan shows also a small increase, but varies mostly randomly. Both the first and the second part of the study have shown that little used and well-stored fan deviate less than fan used on daily basis. There is a significant difference of deviation according to the background test pressure, and this is really something that needs to be investigated, because we would assuming that whether 30 or 50 pascal as background pressure wouldn't make such a big difference. And we have also found out that there is really a need for a requirement on calibration in laboratory to improve the reliability of the verifications, because it's not possible to have laboratories that assess that a fan has a good maximum permissible error while having an uncertainty above the maximum permissible error of the fan. So what shall we do with calibration? That was the main point of this study. This study does not really stress the need for high-frequency calibrations, because it doesn't seem that it deviates a lot after years. There is no big difference, but it stressed the need for a reliable calibration and verification, and above all the first one. So it's better to have less calibration but reliable one than calibration every year, for example, but made by laboratory with a high uncertainty. So what kind of requirements can be set on laboratories? It can be having a measurement capability index above 3 and provide a list of required data and associated measurement uncertainty. So the data to be provided are, for example, given here on the side. And the last question is, what should be done during the calibration? Shall we recalculate the coefficients or only verify, like it is recalculation, like it is done in UK, or only verify manufacturer coefficients, and if they are still good, keep them like it is done in France? We have found out that there is no large difference between the two parts of the study for fan pressure of 150 pascal. However, at the beginning, we have shown that calculated coefficients seem less reliable than manufacturer ones, because when we are changing this pressure for 150 pascal, the results change also a lot. So if new coefficients shall be recalculated, they shall be done with more than 3 points and with a more appropriate regression than just a linear regression. And so it may be better to just verify if manufacturer coefficients remains below the maximum permissible error, and we calculate only if needed, but with more calibration points on a full range of pressure and perform an adequate regression. Thank you for listening to my presentation.